boundary layer with pressure gradient. The flat plate analysis of the previous section should give us a good feeling for the behavior of both laminar and turbulent boundary layers, except for one important effect, flow separation. Prandtl showed that separation, like this figure here, is caused by excessive momentum loss near the wall in boundary layer trying to move downstream against increasing pressure. Which is called an adverse pressure gradient. The opposite case of decreasing pressure, dP on dx, is called a favorable gradient. Right. Favorable gradient. Where flow separation can never occur. Flow separation in a typical immersed body flow such as the figure shown here. The favorable gradient is one of the front of the body and the adverse gradient is the rear, as discussed will be discussed in the later chapter 8. We can explain flow separation with a geometric argument about the second derivative of velocity u at the wall from the momentum equation at the wall, where the momentum equation at wall for a boundary layer we have derived a relation before u the So at wall we have u equals to v equals to 0, but we may have the gradient of velocity on wall. These two parts become 0 and we have this relation for the u at from 2 equals to rho u du on dx minus rho u r equals to the pressure. Then finally we have this relation for the velocity profile. For either laminar or turbulent flow. Thus, in an adverse gradient, the second derivative of velocity is positive at the wall. Let's rewrite the equation here. So let me write again the relation obtained. Is for either laminar or turbulent flow. Thus, in an adverse gradient, the second derivative of velocity is positive at the wall. Yet it must be negative at the outer layer at let me write the second derivative. Rho 2 on rho pi is positive at the ball or it must be negative at the outer layer to merge smoothly with the mainstream flow. So smooth at y equals to delta at the outer layer of boundary layer. It follows that the second derivative must be passed through 0. So in this case we have a 0 point in the equation in between at the point of inflection. And any boundary layer profile in an adverse gradient must exhibit a characteristic S shape. So we have a S shape, for example, velocity profile, which have inflection point. This delta as 0. This figure illustrated a general case. Let me list the various cases in boundary layer existed with the pressure gradient separately. As first case, we have in this figure we have a profile which is very round. So let me write rounded profile. favorable gradient. The profile is very rounded. There is no point of inflection. There can be no separation. And laminar profile of this type. Laminar profile. Mathematically, we can write du on dx there is also another case which we have zero gradients for upstream and pressure and no separation. Let me provide picture. In this case, we have a zero gradient, zero pressure gradient, such as a flat plate flow. The point of inflection is at the wall itself. The inflection point is on the wall. There can be no separation. And the flow will undergo transition. So in this case, we have mathematically round P on round X du and x equals to 0. The third case of the profile is the weak adverse gradient. Let me provide a picture. Weak adverse flow gradient. In this case, a point of inflection occurs in also on wall, on pi. Point of inflection Pi shown in the picture occurs in the boundary layer. Its distance from the wall increasing with the strength of adverse gradient. Distance from the wall related to the from P on round X, and in this case we have mathematically du on dx greater than 0. There is also critical adverse gradient. Let me provide a picture. Critical adverse gradient. Zero slope at wall. The stronger gradient we have also in this case dp on dx 1p on rho x greater than 0. It is defined as the S separation point at wall where equals to 0, separation occurs, because any strong gradient will actually cause backflow at the wall. In the last case, the boundary layer thickness greatly and the main flow breaks away or separates from the wall. This case, the last case in this type of flow, excessive adverse gradient. Backflow at wall, and separation occurring. The flow profile described usually occur in sequence at the boundary layer progressive along the wall of the body. There are various examples in the literature. A second practical example is the flow in duct consisting of a nozzle. Let me write flow in a duct